Good day, everyone. Thank you for so many of you for coming today. Welcome to the first of our 2025 postdoctoral seminars or webinars in this case. I'm Vukosi Marivate. I'm the chair of data science at the University of Pretoria, as well as the PI for the Data Science for Social Impact Research Group. We host these sessions so that people can share, learn from each other, and then we're also hoping that you'll find them very useful. Just for general rules, at the moment, I will introduce Dr. Olaleye. He will give his presentations. If you do have questions, you can type them up in the chat. He will speak for about 40 minutes, and then there will be about 20 minutes of Q&A after that. If they and during the Q&A, we will make sure that everybody can unmute and ask questions. But for now, for the first 20 minutes, that will be switched off, just so that we can keep to a semblance of being able to track everything. All right. So yeah, just introducing Kayode. He's a postdoctoral fellow in our computer science department at University of Pretoria. He holds a PhD in electronic engineering from University of Stellenbosch, where his research focused on using images to train speech models for low-resource African languages. Currently, his work explores speech and language processing for under-resourced African languages, aiming to make language technologies more accessible and inclusive. Kayode is driven by a commitment to supporting linguistic diversity and bridging gaps in technology to understand communities. I also wanted to acknowledge that Kayode's postdoctoral fellowship was made possible through the JP Morgan Scholar Research Grant that we were able to get in the Data Science for Social Impact lab. And he's also been collaborating with a lot of JP Morgan AI team as well. And okay, with that, Kayode, I will hand over to you.
All right, thank you very much, Prof. I'll just quickly share my screen. Can you see my screen?
Yes, and you can go ahead.
Okay, all right. Okay, hello, everyone. Thank you for joining me, and thanks, Prof, for the great introduction. So I'll be talking today about some of the work I've been doing in the course of my postdoctoral fellowship. The title of my talk today is Bridging the Language Gap, Exploring Code Switch Translation for African Languages. Just to quickly highlight some of the collaborators that make this presentation, what I'm going to present today, possible. So we have Dr. Arturo, Dr. Matthew Nambuiselo, Michelle Sibongile, Richard, Dr. Charis, and also my postdoctoral host, Professor Vukosi Marivate. Code switching, just to maybe quickly mention, it's a way of trying to define what I'll be referring to whenever I mention code switching today. So code switching, code mixing, I'll be using these two terms interchangeably to refer to the practice of switching or mixing languages, two or more languages together, within a single discourse. So the focus today will be at the sentence level. As an outline, I'll be talking about why code switching matters. Also be introducing our compact code switching dataset that we created. Also, how we use LLM along with human validation to create the dataset, and also how we assess the quality of the dataset on machine translation. Then I'll give some remarks and also mention some of the limitations of the study. Okay, so why code switching matters? So from the linguistic perspective, say that code switching is actually not an anomaly. It actually represents how many Africans naturally converse. So we have Otundo and Molenze that work extensively on showing this. And also even writers such as novelists, so deliberately use it in their work. This is an example. They use it to capture and reflect South Africans' rich and multilingual reality. And also from the socio-cultural perspective, say an example would be like in some radio callings, like in Kenya and Cameroon, where people will call in to get advice from experts. So we find the experts frequently or occasionally switching to accommodate or code switching to accommodate the callers, just to, carry them along and speak to them in a language that they really understand. So also from the educational perspective, find in some classrooms across Africa, teachers adopting code switching to explain tough concepts to learners, just to facilitate the assimilation of particular difficult concept that they're trying to pass across to the learners. So if we take a look at it from the technological perspective, we see that most companies really have tried to build or integrate technology into their system to kind of understand their customers better. So we see customers interacting with some of these companies online, over the internet, via social media. So we realize that most of the existing machine translation and ASL systems are challenged by, code switching, probably because of its mixed grammar and vocabulary language too, for low resource community. So basically, the system, the MT and ASI system should be developed in such a way that it allows it to kind of, understand and process this like code switching text. So we have these following studies by some team in Kenya that looked extensively into this. But why is it that some models struggle, with understanding code switch text? It's probably because they are not deliberately trained, to process such inputs. And part of the challenge would be the result of scarcity of quality data, as highlighted by Yang et al. And also as highlighted by Winata et al., that most existing data set focus on non-African languages. And also over 60% of code switch data sets are private. So they really publish the paper, but they don't basically provide the data sets that they use to prepare their submission, which makes replicability and reproducibility difficult. Also, some researchers only just provide URLs to download the data because of data attrition. So I think the recommendation by Winata is to identify alternative means to collect written code switch data. So some recent studies have actually showed that synthetic data set obtained from LLMs combined with human validation can bridge this gap. So this will be like the focus of this task would be to kind of show how we go about using LLM alongside with human, to create a compact, high quality code switch data set for 4 African languages, basically. So we have Afrikaans, Sesotho, Yoruba, Zulu. But these are also kind of English-centric. So each of these languages are mixed with English. So we have approximately 120 human-validated code-switch sentences per language. In addition to that, we also have approximately 700 unvalidated samples. Each of these, each of the sentences are paired with English translation, just to make it suited for machine translation downstream task. The domain that we focus on is agriculture. Because it's actually also one thing that's be quite useful, within the African setting. So we target some farming concepts and also provide some practical tips within the data set. We use few shorts in context learning, with GPT for the in context learning feature of GPT-4, followed by human validation to prepare the data set. This is like the workflow that we follow to prepare the data set. We start by defining 5 exemplars with some domain keywords. Then we give these exemplars to a native speaker for the respective low resource language that we are targeting, just to correct the 5 exemplars. Then we use the in-context learning feature of ChatGPT to create some synthetic data set based on these exemplars that we got from the native speaker. Then we basically expand the data set. That means we just regularly curate some more or create some more using the prompt. Then the final results we pass on to a native speaker to validate and basically to correct. This is what the template we use to create the exemplar look like. Basically provide some clues within just to kind of nudge the model, the LLM, towards creating something that will be suited for the agricultural domain. So for the actual prompt template that we use to generate the Afro-CS, we call it Afro-CSXS, we also, just like the same way, provide some clues, basic keywords to guide the generation. We also try to build in some form of linguistic constraints, like the matrix embedded linguistic constraints into the system. So just so that the model can treat the local language, the base language, in this case, the 4 African languages that we consider as the matrix language, and also just treat English as the embedded language. So followed by, within the same prompt, followed by some vocabulary. So provide some agriculture-related keywords. And we also provide the 5 examples, the exemplars that we have validated by a native speaker as some few short examples to further guide the model. We provide some new agricultural keywords, basically, just so that the generation will target some particular vocabularies, that is related to agriculture. Then we provide some additional information just to make sure the model does not generate too short sentences and also not too long sentences. Okay, so in addition to that, we also created some natural and out of domain test sets where in this case, we don't use LLM to generate the code switch sentences. We basically provide a native speaker with some English text, and we ask that they rewrite it in natural code switch format. So we do that also, again, for the agricultural domain, but just to also have some out of distribution test sets. We also generate some for the personal finance domain. So that means basically provide English sentences to a native speaker. We ask that they provide us with the Yoruba English. So for this, basically just for testing, for the purpose of testing the model. Okay, so I provided some samples from like what we obtain. So HEMIA just basically stands for this exact synthetic data that we get from using GPT-4 before human validation. So we then also basically provide the English translation. So we give these two sentences to a native speaker, and they come up with something like this. So where they actually make some corrections wherever necessary. For the natural Yoruba English that we use for testing, we also provide the English, we provide the English sentence to the native speaker, and their goal is to basically rewrite it in code mix format. So in this case, we don't provide any machine generated code switch sentence for the native speaker to correct, but they have to basically write it from scratch. Okay, so to further kind of assess the quality of, or to view some statistic of the data set that we generate using this method, we make use of some code switching metrics. So we have the M index, the I index, and also the burstiness. This author gave like an extensive explanation of how to compute all of this metric. So the M index basically measures how evenly two or more languages are distributed within the text. So values closer to 1 would indicate that the two languages are kind of within a sentence are kind of balanced. For the I index, it captures the frequency of switching points. How frequently does switching happens from one language to another. So a higher index in this case will mean there are more frequent switches between the languages. Then we have the burstiness, which basically reflects how predictable the switching is. So the negative values would imply that the switching is predictable. That means that's like a predictable switching patterns. That means we basically know where the next switching is going to happen. Positive values would indicate like more sporadic switching patterns. That means it's not as predictable. So just to show this metric on our data set of M index, we have the African English set, and also this is the English set has the highest M index. So you can see here, which indicate that the two languages are in more balanced proportion. Whereas for the Yoruba English, we have for the here, we have the machine generated, the human validated. Now for the Yoruba, we have that the machine generated, the unvalidated sentences actually has the lowest M index. whereas for the natural out of distribution set, it actually shows a higher hem index. For the R index, we find most frequent switching happening in the African English sentences, and also more frequent switching happening in the Yoruba out of distribution Yoruba English text sets compared to the not so frequent happening in the machine generated and the human validated form. Then for Zulu English, it has the least frequent switching. So it's represented here. The Bostoners, recently we have it to actually come out negative, as negative value, which would imply that the code switching actually appears to be more predictable. Yeah, happens in more predictable patterns. And and by the linguist, it's actually, this finding actually agrees with the linguistic explanation. That code switching is actually not random, it follows a particular pattern. Okay, so we also compute the part of speech distribution just to have an idea of how part of speech is distributed in the data set. But in this case, we only do that on the English segment of the code switch sentences. But we have nouns unsurprisingly to consistently dominate. We have more nouns in the data set. And also we find that the natural code-switch sentences, that's the Sesotho English and also the Yoruba out of distribution, show more adjectives. Yeah, they show more adjectives than verbs, basically in the English segment. So we have here more, adjectives than verbs. Whereas for the synthetic data, we have actually more verbs. It's possibly maybe because GPT-4 often use English, as an action word. The implication of this would be that in real-world code switching, speakers may prefer their native language for verbs, while in LLM-generated text, they probably favor the use of verbs, English verbs, in the generation. Okay, so to now look at how useful, or if this data set generator using this type of approach is useful, we kind of push it to a machine translation code task, just to assess its performance, the performance of models on models fine-tuned on Afro CSXS on a machine translation task. So we have our experiment set up in this way. We consider two tasks, translation tasks. We have the English to code switch, which applies with translating from English into code switch text. And we also have the code switch to English task, which means translating from code switch to text to English. For our training set, we use the human validated Afro CSXS, which is like about 60 data points. Means we have the code switch sentences and English translation. We also have the human validated set with unvalidated Afro CSX, like the 700 additional data points that we have. So just basically move them together to train the model and to use as a training set. And for the test set, we use the human validated Afro CSX, which is also about approximately 60 data points. And also the natural test set that we compile, which has about approximately 250 Sesotho English, still also on agriculture domain, and about 300 Yoruba English on personal finance. So for the models, we try some large language models. We also try some machine translation first model, MT first model. So for the LLMs, we try Bloom's, Llama, Naya. And for the machine translation models, we try NLP and MATLAB 400. Training strategies, we use the base model, use it as it is, the pre-trained feature of the model. We also try some feature prompting on the model and also LoRa fine-tuning. For evaluation metric, we chose char F++, which is usually chosen for a strong correlation with human judgment. Okay, so maybe now I can provide some of our findings on the experiments we run on the data set. So we have here that blooms actually show significant, improvements after fine tuning, as you see on the blue bar. We see for the base, it's at its lowest form, but as we begin to, inject some examples, like for the facial prompting, it improves, and also here. What actually now helped blooms more is the fine tuning, as like the LoRa fine tuning. We did not fine tune the entire weight. The entire model is just about 15% of the weight, but still we notice like significant improvement compared to the base. And for higher, you notice that higher actually also benefit from the addition of unvalidated synthetic data. So you see in the green bar, where if we compare, there's two, that's for the English to code switch task, we find that higher actually improve. Maybe the improvement is not very noticeable here, but if we look at the other language, like from the translation from English to Sesotho English, we see that the improvement is actually more noticeable. And also the Yoruba, and the Zulu. What we notice there is that not all models actually benefit equally. More data isn't always better, but maybe the reason why more data helped higher model is probably because higher handles noisy data better than Bloom's and also better than the other LLMs model that we investigated. So fine-tuning, we find it to be more effective than few shot prompting. Yeah, we see that in the case of Bloom's, basically the performance improve more significantly, with fine-tuning compared to just some few shot prompting. For the base, we have some copy baseline, just basically to assess whether the model is actually learning to translate or it's just copying English text, compute and just jumping. Computing based on this. So that's like the here. From here, we notice that they actually beat the copy base, always just blindly copying, the input and computing the char F++ score based on that. Now for the other direction, that's the translating from code switch text to English, we find that the empty first model actually outperform the fine-tuned language models. Almost all the cases, actually. You will notice that we did not even actually have to include the results of the fine-tuned machine translation models, because the Afro CSXS dataset did not really improve the performance of this model from the pre-trained performance. So you can even see here that despite just using the pre-trained version of the machine translation model, it basically even beats the fine-tuned version of the language models that we experimented with. So yeah, I would say that machine translation did not actually benefit from fine-tuning on Afro CSXS. And also notice that fine-tuned LLMs, despite underperforming the empty first models, it still should that it beats the copy baseline, in most of the cases. Yeah.
10 minutes.
Okay, thank you, Prof. Yeah, for synthetic versus the natural test set, so we also kind of try to compare the performance of the model trained on the synthetic human validated data set on just throwing it in the wild and trying to see how it would perform. First, still within the agriculture domain, but what we consider natural, test sets, because the human had to actually create the data set from scratch, without seeing what the machine thinks the code switch format should look like. As expected, we find that the model the performance of the model is inferior, on the test, the natural and out of domain test set compared to the synthetic data. And also, relative to synthetic test set, we find that the IA actually performs well on the natural out of domain Yoruba English test set. You see the higher is actually, doing well in some cases. And also the results on English to Yoruba English surpasses the base model. Yeah. So basically we have the results here, on the English to Yoruba here. And English to Yoruba actually beats the base model. So we have the base model here. And for the fine-tuned model that we tried on the out-of-domain Yoruba test set, you see there's an improvement. Yeah, what are some of the common errors that we observe? In this direction, the translation like Yoruba English to English, translating from code switch to English. Some of the errors we identify is the model. In this case, we have the sentence, the target, it looks this way, but where Bloom's actually makes this word. So it uses check here, but Bloom's use monitor. It uses healthy here, which is actually not in the target. Whereas NLLB, you find it's actually used the exact word. I think it gets it right in most of the cases. But we may say that maybe the error is not, though it's better, Bloom's is penalized for this type of error, but maybe it might not be completely false because the monitor appears to be semantically related to check, and healthy also in some sense appears to be semantically related to suitable. Another error we observe, especially when moving from English to Yoruba English, that's from English to code switch sentence, is that for the accented languages like Yoruba that uses diacritics and tone marks, we find that Bloom's actually respect the choice of tone marks that it finds in the Afro-CSXS dataset, whereas the NLF will completely ignore that and just default to the full diacritic markings. That is probably more pronounced in its pre-training dataset. Based on some remarks, we find that Afro-CSXS actually fills a gap. It provides like kind of much needed African code switch data sets that we actually created using LLM with some human validation. We find that how fine-tuned LLMs actually improve their translations. High quality small data sets can be said to actually be useful in fine-tuning large language models, but the same cannot be said for the machine translation first model. Yeah, as it does not really benefit from, the small size Afro-CSS that we use to fine-tune it. Synthetic data also impact varies by model and language. So we find some models benefiting more than others, like Kaya benefiting even more from the addition of validated synthetic data sets, whereas Bloom struggle with this. So for continuous effort to optimize the synthetic data generation and also to incorporate more human validation. Maybe some limitations of this study be like the scope of the code switching that we investigated in this study is basically limited to Yoruba, African, Sesotho, and Sezulu. It would be beneficial to kind of include more languages to demonstrate the generalizability of our conclusions. And also the focus is on English to African languages pair. Maybe sure should consider African to African language switching. So instead of using English as a pivot, we basically move from one African language to the other, because switching does not only happen, between English and African language. Some cases it happens between two local languages. So maybe to be more useful to kind of investigate this future work. And also human validation that will plug into the generation is definitely useful. You can see it shows some potential for quality improvement, but it's also not without risk. It's liable to subjectivity in the validation process by human, like human might just decide to, favor their own linguistic preference. And also maybe the expertise is also might not be enough, as the native speaker may not necessarily have a full understanding of, how to actually translate the sentences to a correct code switch format. But these are basically some of the limitations that identify in the work. These are list of references to studies. And yeah, that was my presentation. Thanks for your attention.
All right. Thanks a lot, Kayode, for that. That was very informative, and I think a lot of people are it's always interesting thinking about code switching. It's a tough space, but maybe before other questions come up, where do you think this goes from here? And then if you have a question, you can just raise your hand. I will acknowledge you and then call you out, and then you can unmute to ask your question. But yeah, okay.
Okay. Yeah. Well, I think there is a couple of things can follow. Could be maybe more rigorous testing of the performance of the model, in terms of also bringing humans, into actually use the model, the result of the model, and try to actually, assess the quality of the sentences, that's generated. Another thing is to basically try to see how we can inject more of findings from that metric, the code switching metrics that we show, into the synthesizing process. As it is now, we now really put back much of the findings, the statistic that I showed in the code switch, the Afro CSX, MI index, high index, and the burstiness. So maybe it would be also interesting to kind of, see how much of the things we learn from this statistic that we derive from this can be pushed back, into maybe improving quality of synthesis by LLMs before now even maybe thinking of also bringing in more humans to kind of help with the validation process, just to kind of remove that biasness that I mentioned, where the quality is kind of at the mercy of the annotator's bias, to a specific linguistic, preferences. So yeah, that's like maybe two of the things that can be.
All right. Thank you. Tapelo.
Good afternoon, everyone. Am I audible, Prof?
Yes.
All right. Thank you, Dr. Kayode, for this wonderful presentation. I just have a small question to you. You touched a little bit on the fact that your research actually shows that your code switching isn't really random. It happens like by some reason or some something that's it's actually followed when people code switch. Can you quickly go back to that and explain a little bit more on that? Because I kind of missed it. I just heard you saying it, but I didn't really see the results. And actually, what kind of proof told you that code switching doesn't really happen randomly? Because in linguistics, they actually show that it doesn't happen randomly, but in computer science, we haven't really, I haven't seen any paper talking about code switching not happening randomly.
Yeah. Thanks, Tapelo, for the question. Yeah, actually, there is that kind of mismatch in the understanding between the computational linguist and the theoretical linguist. So the claim by theoretical linguists is that code switching is not random. But computationally, you find that most of the papers that are published on this, you find that the conclusion is usually that the code switching is like unpredictable, like the pattern is unpredictable. So that's like the kind of mismatch that currently liable to. But maybe one of the reasons for this, for the claim by the theoretical linguist, the reason why they come to that conclusion, because you even find in this paper that I reference there, says even when it looks like the switching is happening in bursts, that is not like predictable, you still find that switching, when people code switch, it's a conscious effort. So they choose when they want to, what settings and how they want to go about it. But yeah, as you rightly pointed out, in most of the computational studies on this, you always find out that the finding is unpredictable. But now, as far as Afro CSX is concerned, the reason for this type of chart here could be because, as you have seen in the course of the presentation, that we make use of native speakers to help with the creation or the correction. So there is already that background knowledge that here is the task. Your goal is to make it code switched, comparison. So there's that, tendency to probably want to follow a specific way that always results in code switching. So that could maybe be the reason for this form of more predictable, pattern that we see in Afro CSXs. Yeah. I don't know if you're satisfied with that
Yeah,
answer.
I am, Doctor. Just a follow-up question on that. So once you determine that actually code switching can be predicted in some sense, can you then later on check what kind of words are then potentially going to be used for code switching? Because if you can predict it, then it means you can figure out the words that would come next, or the words that are typically used for code switching. Is that a possibility going forward? And
Yeah. Go on. Maybe you should try to clarify the question just to make sure I understand you.
oh, okay. So based on like these results that you've just shown right now, it says that code switching is predictable, which means that it's not completely random. If that's the case, because I understand that code switching happens when people use certain words to maybe complete a sentence. Can you then later say, now I'm trying to predict what kind of words would be predicted in a particular sentence? Am I making any sense? There's someone in the background.
Yeah. Yeah, maybe just to attempt to answer your question. Bustiness in this case does not necessarily refer to the choice of words used, but more in terms of the busting, maybe bustiness is So just to check whether switching happens in burst or at maybe more predictable pattern. So for example, maybe if you go through 5 sentences, one paragraph, you may not find any switch from the dominant language. Whereas for anti-bustiness, it means that as you are going through the sentence or the word, you are most likely sure that, the switch is going to happen. So that means you're going to move from the one language to another. So it's probably not more related to maybe the choice of word used, but more in terms of the, just moving from one language to another, So that's like what the bustiness tries to show here. I believe there probably be some other way to kind of inject particular word and, by a choice of vocabulary, dictionary that you're using. But yeah, I think that's just like my unwavering answer to your question. Yeah.
Okay.
Right.
Thank you. Thanks for that, Olufemi.
All right. Can you hear me? Am I audible?
Yes.
All right. Yeah. Thank you so much, Prof. And thank you so much, Dr. Kayode, for the amazing presentation. I'll just ask 3 quick questions. While I joined about 10 minutes into the session, so I wasn't sure if you already talked about the type of code switching, whether it was intra or inter, or a mix of both that was done in the experiment. 2 is also, I was curious, how did you find the code switching points, you used for, the I index, M index, and some of those, indexes you calculated? Was it collected, during the data gathering process, or did you use some kind of, code to, find where, the code switching points were? And the last question is maybe it's still centered around what, the previous questionnaire asked, is, the AI generated or LLM generated code switch sentences are usually not as natural as one would say it. And you have already also mentioned that, in fact, code switching also depends on the context of the person. One could be skewed towards English or skewed towards the language in question. So I don't know. The question really is, did that affect, any sort of the results that you had? Or did you notice maybe there was any, disparities in, the AI generated and the natural code switched sentences.
Yeah. Thanks for your question. Yeah, I think the first question, if I remember, is about the type of code switching,
Yes.
right?
Yes.
Yeah. So yeah, I'll say it's intra-sentential in this case because we're looking at this at the sentence level. Okay, so it's basically you have switching within a sentence, like from one language to another. So it's in a sense an intra-sentential code switching. The second question,
It was how
maybe.
you found the code switching points, whether you collected them at the
Oh,
point of
yes.
or
So
actually.
basically, yes. So basically, there are formulas to compute this. So it's after collecting the data set, we have some scripts that we've written just to compute and plot, the numerical values, basically. So it's, there are formulas to compute this. And I think you also find that sorry, from line this reference, Guzman et al. Yeah. And maybe your last question is about what kind of anomalies
Did you notice?
notice.
Between the
Yeah, I think there's a couple. Actually only presented some examples on Yoruba English because as the kind of the language that I understand. So this is one of the examples that we will see. We find that the model is basically sometimes get too robotic, like just begin to throw in some words that are not supposed to be there. Like I know you speak about, if you read this, you'll find that it's just some word that shouldn't even be there, in the first place. Yeah. And also you see, if you read the way it switches, it's kind of also robotic. It doesn't sound written naturally, compared to after trying to correct it, in this sense. So these are just some of these. So in some cases, it just completely mess things up. Like, in fact, sometimes it returns back just English sentences, to you. Yeah. And so this is why in our generation, we try not to generate so many sentences at the same time. So if you find in the prompt, we limit it to 30 sentences per generation, just so that the model does not start to hallucinate after some time. Yeah.
Wow. All right. Thank you so much, Doctor. Thank you.
Thank you.
Okay, Jacob.
Thank you, Prof, and thank you, Dr. Kayode. Mine, I just want to ask in regards to the quality of data and just taking into consideration some nuances. So first of all, you mentioned like one of the studies was about code switching in Kenya. So I'm actually from Kenya. I wanted to ask, did you take into consideration the fact that code switching also occurs based on the areas? Like, for example, like the urban setting would encourage more code switching, and not because we understand our native languages, but because we cannot be able to converse fully in what I would call our mother tongue, so necessitating us to use code switching. And then that would also be, let's say, transgenerational, so that you'll find like my father's way of code switching is different from mine because of that aspect that he was more conversant in our native language than I am, because we grow up with English, and then English becomes like our primary language, and then our mother tongue become secondary language. So that has an impact not only on how much we code switch, but also on the quality of our languages. Like I would speak my mother tongue in a can I say poor way, and so that kind of data may not be the best, because I'm assuming you're Yoruba. You find that maybe you will not speak as clear Yoruba as the people before you. So how does that affect the quality of your data? And secondly, my question is regards also when we code switch a lot, we find ourselves using slang. So do you take into consideration that the slang interferes with the quality of data? Because now some things become now that there are words we use which are slang, which are not formal language, but they've become sort of standardized way of saying things. Like, for example, in Kenya, if you say juala, which is a plastic bag, it's a slang, but it is a standard language, sort of, can I say, standard now way of calling a plastic bag. Thank you.
Thank you, Jacob. Yeah, as far as the study is concerned, there's several other nuances that may not have been captured because of the limited number of humans that we have in the loop. But yeah, as you rightly pointed out, it's code switching can happen as a result of different reasons. So if, for example, we give it to maybe an educated person that is fluent in both languages, the way they will produce the switching might be different from maybe someone that use code switching not because of just trying to be identified with a particular group of people or because trying to explain a difficult concept to a learner, but just because, yeah, they must express themselves to this to this person that happens to be monolingual, only understand English, for example, but they also understand the vocabulary, in English. So they just, because of the need to express themselves, they try to throw in some. Also, that is more like situational. So yeah, we did not put into consideration all of these different nuances in the data set, but just like we make the focus to be on agriculture, we see that most this currently, I don't know how many people are still going into agriculture, try to do farming and all of that, probably targeting white collar jobs and all. So we find that most in some African settings, most of the farmers are probably uneducated. So to make this kind of model really useful, which I believe it should definitely target the group of people, So maybe this will go to first question that, Prof asked, where do we go from here? It's just basically now to prove like the quality of the data set, in terms of try to cater for different groups of people, in data sets. For your second question, sorry, I don't think I caught your second question.
I was just saying the impact of slang, slang.
Oh, yes.
The impact of slang on code switching.
Yes. So yeah, it's definitely also another nuance that needs to be also considered. But I don't think there's currently like a standardized, way of switching that is probably published in the literature to kind of help to classify code switching, what's stands as code switching and what shouldn't be considered as code switching. But yeah, definitely to make this type of tool useful, need to bring in some slangs and some other local content that might only be relevant to people within that community. But maybe the closest to that in our prompt is just we added that keyword cultural. So the generation should be culturally relevant, So in this case, it basically will be able to capture some of the, slangs. In fact, as another project that we're also currently considering is also especially for the financial domain, is currently building a list of slangs that people use within the financial setting, basically. So quite a number of them. So one way is to to fortify the prompt is to kind of serve some of the slangs as the keywords, the domain-specific keywords that would provide within the prompt. So this will help the model to actually generate, sentences that, consider some of the slangs. In fact, in one of my preliminary, tests to this, I find that the model actually, especially GPT-4, actually recognizes some of the slangs and is able to kind of inject it into the sentences. So yeah, that would be my response to your question. Yeah.
I think the last question, I'll take Evelyn's one. There was a comment from Marissa that, okay, a more comment for you, Kayode, you can just check the chat, that maybe using WordNet might assist because it can provide different like synonyms and explanations. From Evelyn, the question was on the use of metrics in training and generation. Is it possible to train a multilingual LLM and force it to code switch using a known code switching frequency? Right, so can you train a model that specifically will be code switching, given some statistical properties that you wanted to keep?
I think from preliminary results or findings from what we showed, I don't know if I'm able to show some of these examples. We find that for the Bloom's model, which is actually, well, not as sophisticated and also not as big as the Llama higher models that we tried, we find that with that small fine-tuning, about 16% of its weight is fine-tuned, and we find that the model is actually able to code switch. That's the task, the English to code switch task that we also investigated. So we find that the model is actually able to code switch, but there has to be some way to direct it to do such, So these are instruction chain model, like the large language models that we try, Aya, Bloom's and Llama. They stand, it's easier to fine-tune them, to tweak them, to be able to pursue than the empty force model, because one of the things we found out with the empty force model that we investigated is that usually in most cases, just if you ask them to translate from English to a code switch sentence, they just return back the English sentence to you. Whereas for Bloom's, it stands a better chance as adjusting its weight to be able to respond, to such prompt. So yeah, I would say with my additional work, it should be possible to push, the model in that direction. Yeah.
Okay. I think with that, we will close. You can stop sharing, Kayode. Thank you, everyone, for coming in today. This was the first in our new series that has just started. We will have another speaker next Wednesday as well. It will be Dr. Idris Abdulmumin, who will then think. So watch out tomorrow for the invitation, and then you can RSVP again with the information in that space. We know that we would need much more time. This is one of the most fascinating topics within at the moment, dealing with language within the continent, and I'm guessing even further than that. So it's very appreciated, Kayode, and it's been great to. I think there's a lot of text and comments. I'm hoping the chat stays alive so you can still respond to people via the chat in those space. But in terms of the webinar itself, it is done. So thank you, and yeah,
thank you.
See most of you next week as well.